Hello, we're the joint Brown University and Rhode Island School of Design team working on TEST-RAD, Tufted Electrostatic Solution to Regolith Adhesion Dilemma. TEST-RAD was created as an answer to the problem that has troubled moongoers for the past century. How do we keep dust out of, well, basically everything? Lunar regolith is small, abrasive, and poses a huge risk to astronaut safety and the success of lunar surface missions. TEST-RAD combines tried and tested electrostatic applications with novel fiber designs to present a unique approach to the regolith adhesion dilemma, providing both passive blocking and active repulsion to add just enough protection to keep our astronauts silica-free, equipment clean, and everyone back home with a peace of mind. Our team is the result of a year-long collaboration between the Rhode Island School of Design's Space Design team and Brown University's Brown Space Engineering, two groups full of passion for space exploration. We are composed of an interdisciplinary group of engineers, designers, and more. Coming from a diverse background, we strive to combine disparate ideas and very different design approaches into the novel design that became TEST-RAD. TEST-RAD aimed to provide a solution to regolith proliferation through its hybrid mitigation approach, utilizing a passive fiber design coupled with the active electrostatic generation assembly. Our team derived the solution by researching natural techniques to dust mitigation and tufting techniques, as well as looking to past successful electrostatic applications, combining these concepts into a layered dust repulsion system with tufted fibers and an electrostatic component meant to maximize protection of the equipment and dust repulsion. TEST-RAD thus aims to address issues including mechanical wear, dangers posed to astronauts' health, and hindrance to experimental equipment due to regolith on the lunar surface.
TEST-RAD's initial inspiration came from nature, specifically the chinchilla, a rodent with the densest fur of any land animal. Chinchillas have 60 to 80 hairs per follicle. Should a chinchilla get wet, the water would have a very difficult time being able to escape the fur, leading to matting or even rotting. In nature, chinchillas instinctively roll themselves around in volcanic ash to bathe. In captivity, they take dust baths. These chinchilla dust baths are what inspired TEST-RAD. TEST-RAD's technology acts as a hybrid mitigation system, providing both a passive barrier to lunar regolith, as well as an active electrostatic component that assists in the repelling of any charged lunar regolith. The system is composed of 6 parts: charged fibers, catching fibers, metal mesh, insulative backing, charging wires, and an ionization device. An outer layer of tufted conductive fibers repels the same charged regolith. These fibers are arranged in multiple densely packed rows that spread out at the top to bridge the gap across a juncture. These fibers carry the same charge as the regolith, extending the electrical field and decreasing the amount of dust accumulation. Short catching fibers, placed along the internal edge and only exposed in the event of the opening or closing of the seal, act as a secondary layer of defense, catching regolith particles that get near the surface of the seal or edge. During donning or doffing, or other opening and closing operations for alternative applications, regolith particles could be shaken loose, potentially physically bypassing the charged fibers. Due to the presence of the catching fibers, the regolith particles that land along the seal abutting edge during the opening of the juncture would be caught by this row of catching fibers. Both types of fibers, conductive and catching, are tufted through an expanded copper mesh. Charge delivery wires from an ionization device attach to the copper mesh to provide the system with a static charge. An insulated backing, made of Kapton film, connects TEST-RAD to the apparatus and insulates it from the protected equipment. Mark 2.3 is pictured here. It was one of the 12 distinct prototypes of TEST-RAD. Marks improved upon one another in material, fiber attachment method, and in the static generator used. Pictured above is Mark 4.1. This most recent prototype used Liberator Vectran by Rhode, a multi-filament yarn spun from liquid crystal polymer for the conductive fibers. The shorter catching fiber row along the abutting edge used polyester fibers. In its current state of development, the material costs to prototype the first 10 cm of TEST-RAD costs $528.74, and each additional centimeter costs 24 cents. TEST-RAD measures 1.3 centimeters tall with a linear density of 1.45 grams per centimeter. TEST-RAD was originally proposed to be placed on the spacesuits of NASA's Artemis mission. However, if TEST-RAD cannot be put onto the XEMU suits or the commercial suits flown on the early Artemis missions, we have considered other applications where the use of the technology is appropriate and valuable. The decision was made to use TEST-RAD as a strip to ensure adhesion, coverage, and flexibility. This flexible tape-like format also allows versatility in application. TEST-RAD can be considered in application for many other closures, seals, and appropriate edges or junctures on equipment that have unresolved need for regolith mitigation. Our suggestions for appropriate applications of TEST-RAD include the Viper battery cover, gearbox covers, and the mirror and lenses of mission cameras. Above is pictured a rendering of TEST-RAD as it would be applied to a gearbox. Mark 4.1 is applied to an IP67 rated junction box, approximating the gearbox application. TEST-RAD holds great promise for the gearbox to prevent regolith-induced wear and tear on the internal mechanisms. Mark 4.1 is pictured here, open, and on the next slide, closed. All junctures on the gearbox used for service access or areas with vulnerable edges could benefit from this gearbox-style application. Another promising alternative application of TEST-RAD is along the seam of the Viper battery cover. Regolith can cause the battery to overheat either through permeation through junctions or creating a film over the surfaces, leading to a larger system failure. Previously, there was no specific dust mitigation protocol in place, meaning that astronauts had to manually brush regolith off of the battery cover. TEST-RAD can be applied here as a dust mitigation strategy and would line vulnerable seams and junctions of the battery cover, preventing dust permeation. TEST-RAD can also be applied to the cameras monitoring crater formation below the lunar lander, such as the SCALPS camera. These cameras, designed to film the lander crater and landing thrusters, are bombarded with regolith. Thrusters launch particulates off the moon's surface, making these cameras particularly at risk to lunar regolith.
For verification testing, we use the simulants OPRL2W30 and OPRH2W30, which were manufactured by Off Planet Research LLC. Both of these simulants contained particles in the required size range, 50 to 0.5 micron, but they also contained much larger particles that impeded initial testing. Due to these large particles, our team filtered the simulant to create general use Mars simulant from the former and general use Highland simulant from the latter. The filtering process consisted of adding water to the simulant, passing the mixture through a fabric filter, and boiling off the water at the end. These simulants were used for all high-fidelity testing, while our remaining unfiltered simulant was used for initial experiments and testing various experimental procedures. To simulate the charged characteristics of lunar regolith, we used an ion-fixed static generator from TAC Industries to generate a static charge on our lunar simulant. During verification testing, the static charge was transferred to the lunar simulant by spreading a thin layer of it over a metal plate charged to 30 kilovolts by a TAC generator. Our team purchased two such generators of opposite polarities so that we could measure TEST-RAD's repulsion capabilities during simulated lunar day and lunar night. The simulant charging apparatus was constructed with close proximity to each testing apparatus to ensure that charge was not lost when transferring simulant between charging and testing apparatuses. Tests with the Faraday cup shown here confirmed that the simulant charge rapidly dissipates on Earth in laboratory conditions, so building the apparatuses together was required. Verification of our technology was conducted within a glovebox inert gas chamber environment, using high-fidelity simulants throughout the prototyping and testing processes. TEST-RAD was tested within the chamber and was subjected to various regolith mitigation tests. Ultimately, for verification testing, we used a glovebox chamber manufactured by Terra Universal Incorporated. This decision was made in order to achieve an isolated environment using inert nitrogen gas to push out ambient air. This allowed us to achieve an isolated environment for the majority of verification testing. This glove box was also equipped with outlets allowing us to charge both the prototype and the lunar simulant simultaneously. The vacuum glove box we purchased did not have such a power supply, so in order to conduct the entirety of our testing, we only conducted our junction box tests within the purchased vacuum box, which could achieve a vacuum of 0.01 atmospheres. These tests were prepped for by achieving the box's maximum vacuum and subsequently flooding it with inert gas prior to testing. These chambers provided the necessary laboratory environment to reach TRL4 because they provided an isolated environment with charged lunar simulant and lower humidity. Preliminary testing showed humidity had a large impact on simulant charge retention. Low humidity levels were achieved with partial flooding of inert gas in the Terra Universal glove box and complete flooding in the vacuum glove box. From an ambient partial pressure of water vapor of 1.87 kilopascals, we were able to lower this value to 1.57 kilopascals in the Terra Universal glove box and 0.297 kilopascals in the vacuum glove box, respectively. If the project continued over a larger time frame, we would have performed additional testing in a vacuum chamber in order to demonstrate TEST-RAD's performance under conditions more closely resembling the lunar environment, achieving a higher TRL. 3 tests referred to as the passover test, push test, and saturation test were performed in the Terra Universal glove box, and 2 tests referred to as the junction box test and failed seal test were performed in the vacuum glove box. Initially, we used variable amounts of simulant charging time to check how repulsion varies with voltage, but preliminary tests showed this had almost no effect, so we generally waited for less than 30 seconds. The output voltage from TEST-RAD attached to a remote ion generator from Jackson Control's Aircoy 30M was approximately 7 kilovolts for both positive and negative charges. We assumed that TEST-RAD maintained this charge for all tests, not including controls where there was no charge on the device whatsoever. The passover test involved passing TEST-RAD approximately 3 centimeters over a simulant-covered charged plate, with both possessing the same charge. We repeated this passover, moving TEST-RAD across the simulant-covered surface 5 times. After the completion of the 5th, we would calculate the amount of simulant that was repelled by the system by mass. The purpose of this test was to determine if TEST-RAD was effective at repelling dust that did not come in direct contact with the system. This test intended to model how the apparatus that TEST-RAD is attached to will interact with levitating charged clouds of regolith on the moon. This levitation occurs due to the same charge repulsion coupled with low gravity across the lunar surface as well as astronaut activity. The push test consisted of pushing positively and negatively charged simulant directly from the simulant charging apparatus onto TEST-RAD, with the distance of the furthest particles recorded. This test simulated the regolith coming into direct contact with TEST-RAD and showed how the system is capable of repelling dust a significant distance away from a given apparatus. This would be a common occurrence on the lunar surface, especially if TEST-RAD is used on something near the ground. The saturation test measured the limit of how much dust particle mass can be retained by TEST-RAD. The fibers were detached from the electrostatic system and their mass was recorded before being placed in a container of simulant. This container was then shaken to simulate rough impacts to the system. The fibers were then taken out and their mass recorded again to calculate how much simulant was picked up. This was meant to give an upper bound of the regolith holding capacity that might limit TEST-RAD's mitigation capabilities. The junction box test was designed to check if TEST-RAD could prevent dust from accumulating in sensitive areas of a given apparatus. Our team utilized IP67 rated waterproof and dustproof ABS junction boxes for this experiment, where one was treated as a control and one was outfitted with Mark 4.1 of TEST-RAD. It was performed in the vacuum glove box flooded completely with nitrogen gas, and by placing the 2 boxes in a shallow tray with the top and bottom lids of Mark 4.1 charged by 2 nearby ion generators. Approximately 400 milliliters of Highland simulant was then poured over both boxes. Each junction box lid was lifted vertically and placed back down 20 times. Lastly, the boxes were removed and the rims of the 2 boxes were compared qualitatively. This test was meant to demonstrate TEST-RAD's capabilities on the edge of an opening piece of equipment or cover, such as the Viper gearbox. The last experiment is the failed seal test, which has the same setup as the aforementioned test, except that there are small balls of tape on the 4 corners of the inside of each junction box. This was done to create a small gap in each of the boxes that they would each have a small opening around their perimeter to simulate a sensitive area or a seal that has failed and begun to open. In the vacuum chamber flooded with N2, we took the 2 boxes and rotated them on all 4 sides while pushing them into the simulant. We then removed the boxes from the chamber and checked the interior to assess how much simulant had gotten in through the openings. Tests on the system showed that the mean distance repelled was approximately 23 centimeters of particles in the 50 to 0.5 micron range. Additionally, testing showed that at a distance of about 3 centimeters from simulant, TEST-RAD could repel a mean of approximately 30% of simulant in that same particle size range. These tests also had a maximum average value of 29 centimeters repelled and an average maximum value of 66% repulsion at the 3 centimeter distance. The failed seal test, meant to illustrate a non-ideal seal, showed that TEST-RAD is more effective at keeping dust out of a seal area compared to no protection. We believe that these results indicate that TEST-RAD is a versatile dust mitigation device, which can then be integrated into various Artemis instruments. To reach the lunar surface by the year 2026, a series of testing milestones and design changes would need to occur. The path to flight would involve the following developmental stages: an initial 2-year implementation phase focused on testing and continued research in various relevant environments. Next, there would be a year-long integration and verification phase in which designs and systems are finalized and the testing of TEST-RAD fully integrated into its system would take place. Lastly, a year-long recombination and flight preparation phase would occur, in which the technology would be prepared for launch and use on the moon. We would develop methodologies and procedures to be used on the moon to ensure TEST-RAD's safe and effective use and test the system for stresses faced during flight, transportation, and landing. In the first stage of this development, we would continue to test the system to determine if critical design changes are necessary. For example, given the size of our prototypes, it was not essential to have multiple charge-producing units connected to TEST-RAD, but we would have to test the logistics of a larger prototype given possible applications requiring this as such. These tests may reveal that additional charge-generating devices may be needed to sustain charge density. Furthermore, we would continue research into forms of bipolar charge generation to determine if there is a more efficient charging or charge proliferation method, requiring a revision of our testing protocol, as the voltages would be higher than what we can currently safely test with our equipment. In order to continue to determine the level of effectiveness of the system, we would conduct testing in replicated lunar surface conditions. We would also conduct higher and more refined levels of long-duration testing to guarantee TEST-RAD's effectiveness throughout an extensive mission and advanced safety analysis. At the end of this implementation stage, a critical design review would evaluate the quantitative data gained from the system and TEST-RAD's possible role in lunar missions. After the design review, if it is determined that there is a concrete and mission advantageous place for TEST-RAD in the Artemis missions, we would specifically tailor our design to that best use case. At this point, it would be evaluated if any of the design changes investigated in the first phase would need to occur to fit the new application, such as length and charge inputs. If so, those modifications would be made. Then the new model would be tested along with similar parameters as before, analyzing if the changes impact TEST-RAD's capability to repel dust and mitigate other regolith-associated problems. Afterwards, application-specific testing with a fully integrated model would be done to analyze TEST-RAD's mitigation properties in a simulated lunar environment, complete with low pressure and temperature ranges reflective of the moon's polar regions. Following this year-long integration and implementation phase, we would conduct a complete analysis of our data and the position of the system in the lunar architecture. If our team and Artemis personnel see TEST-RAD's benefit and guaranteed success in the lunar environment, we would move into the recombination and flight readiness phase. In this phase of the process, we would conduct continued analysis of the system with a focus on the stresses it would face during launch and landing, the sequence of operations for the installation of the system, and a baseline level of test to ensure the safety and effectiveness of the system after installation on the moon's surface. The proposed objective of our project was to produce a hybrid mitigation device that provides both a passive barrier to the lunar regolith and an active electrostatic component that repels charged regolith from the surroundings. Through our verification testing, we successfully validated the use of the fiber system's passive blocking abilities. This passive mitigation strategy is effective on various applications that utilize seals. Additionally, we achieved our electrostatic generation assembly's proof of concept for active repulsion cases, as shown in the data from the push test and the passover test. However, we believe further research is required into the active repulsion of charged particles, primarily due to the limitations that the electrostatic charging method employed to charge the simulant. Simulant charging, while effective, was only achieved under specific setups, which ultimately limited our ability to conduct testing efficiently. Using the conductive plate to ionize the simulant directly, we defined a series of experimental designs in which TEST-RAD's active repulsion is proven and effective at mitigating dust. The passover test, which was meant to show the long-range repulsion ability of TEST-RAD, successfully demonstrated that. The push test, which simulates the interactions that happen when Regolith comes into contact with TEST-RAD, showed that particles are repelled, some at a very great distance, which is another success of the project. Looking at this data, we can conclude that our design makes a low-cost mitigation solution possible. While sacrificing the efficiency of a comparable electrodynamic repulsion system, the low cost of fibers and ionization devices allows for a cost-effective approach that is easy to replicate and replace. Moreover, versatility in the integration process and the simplicity of attaching TEST-RAD externally to devices can keep implementation into established applications simple, shortening the time required to do that. In addition to that, the active repulsion properties of TEST-RAD from the tufted fibers are more remarkable than initially anticipated. Further research into a higher quality EGA that can safely utilize higher voltages is necessary for the electrostatic approach to be completely viable as a lunar regolith mitigation strategy. Both systems must be verified in conjunction to deem TEST-RAD's hybrid approach entirely successful. Beyond the scope of our project, functional repulsive capabilities using the EGA were not proposed initially, but were found to be quite effective throughout our testing. If researched further, the use of a high voltage static generator with the EGA can provide further regolith mitigation and cleaning strategies that were not explored through the use of TEST-RAD. Numerous consecutive trials that occurred during verification testing necessitated constant cleaning of the prototype in a similar manner that would occur on the Moon. We found that frequent and thorough cleaning was easily achieved, and therefore TEST-RAD could present a potential pathway to decrease overall equipment cleaning time. In the long run, these strategies should reduce the harm done to equipment and astronauts by regolith. Another advantage of our system is that the best performance of TEST-RAD in our verification tests occurred with the conditions that will be the most similar to the lunar landing locations chosen for the Artemis missions. The extremely consistent results found in trials using the Highland simulant lend credence to its success for an eventual use case in the highlands of the lunar South Pole. As humanity begins to establish its permanent presence on the Moon, there will be many problems unthought of that we will need to solve together, technical and otherwise. We hope that TEST-RAD and the spirit of innovation and collaboration behind it, Brown and RISD, nature and engineering, and even passive and active dust repulsion, can continue as we travel further and further away from the small blue dot that we call home. We would like to thank everyone who helped us throughout the duration of this project. We could not have gotten to the place we did without the immense amount of support we received from both Brown University and the Rhode Island School of Design. A special thanks to our advisors, Rick Fleeter and Christopher Bull, for their assistance throughout the entirety of this challenge. We'd specifically like to thank Derek Stein and William Patterson for physics and electrostatics consultation, as well as Nancy Simonelli, Pete Schultz, and all of the Rhode Island Space Grant Consortium for their support throughout the entire process, especially with funding. We would also like to thank John Shilko for allowing us to use his lab space on Brown University campus, and Paul Waltz for guiding us through the process of securing research space in the midst of the pandemic. Lastly, we would like to thank Jackson Control for generously providing us with one of their Aircoy 30M bipolar ionizers free of charge.